Okay, I'm going to start. So I'm Curt Cutler, and I'm going to try to describe for you in this half hour a new version of the F-statistic, which I think should be a better detection statistic for searches for all-sky searches for gravity wave pulsars than what's currently used. What's currently used is something for all-sky searches over very long data sets of months to years is something called the semi-coherent F-statistic. You would use the coherent F-statistic if you had infinite computer power, but instead one uses a suboptimal one called the semi-coherent one. What I'm going to do today is describe yet another version, which I call the phase-relaxed F-statistic. Right. Which has some of the same flavor of the semi-coherent F-statistic, but I think it actually captures the physics considerably better. And because I think it captures the physics better, it ends up being more sensitive as a detection statistic than the semi-coherent one by, and I roughly estimate this, by something like 10 to 15%. And that's a rough estimate that I have to improve, but I just wanted to give you some idea of what's at stake in the talk. It's not a revolution, it's not even a factor of 2, it's probably something like 10 to 15% in amplitude sensitivity, which is maybe factor 50% the number you can see, something like that. Okay. So this talk is going to be pretty easy to give because there are only really two take-home ideas. One, I just going to define for you this new phase-relaxed F-statistic and show you the motivation. And the motivation is very physical. So as soon as you know the motivation, you can understand the definition. And the second, well, just because you have a new statistic doesn't mean you can calculate it efficiently. Just by looking at the statistic, it's not obvious that you can. But in fact, I didn't find a very efficient way of calculating it, which I think is also pretty cute. So I'm going to show you how you calculate it efficiently. Before I do that, I just have to give you some background material on the coherent F-statistic, the semi-coherent F-statistic. Then I get into the new stuff. And finally, I'll give you some just sample results showing you how it works and how it compares to the semi-coherent F-statistic and discuss some future work. Okay, the fully coherent F-statistic. So imagine you're looking for a pulsar with known or assumed sky position up there, and assume that you know, say, the frequency and frequency evolution. So then the only unknown parameters are 4. So the overall amplitude, the inclination angle of the pulsar, its polarization, which is also related to the direction of this pointing of the spin, and then some overall phase, which is related to at time t equals 0 exactly where it is in its rotational motion. So there are 4 parameters describing the pulsar. And in terms of these parameters, the gravity wave signal is nonlinear. But the whole trick behind the F-statistic is you can make a change of variables from h0 I iota psi phi naught to lambda 1 through lambda 4, such that h of t is actually linear in the new variables. It should be easy to see why. If I imagine, say, a signal of fixed frequency coming towards me, say it's a scalar field, then there's just a two-dimensional vector space, the sine quadrature and the cosine quadrature. Because gravity has 2 polarizations, both the plus and the cross have a sine and a cosine. So they're just then, so the plane wave coming towards you has to be describable by just 4 parameters, and there's a simple relation between those and these, but I'm not even going to write it down because I don't need it. Okay, so these are now the 4 basis waveforms. By the way, everything I'm going to say easily generalizes to n detectors, but I'm just, to make it a little bit simpler notationally, I'm going to be mostly talking about 1 detector, right? To ease it. And then what you have is a piece for the plus polarization and the cosine quadrature, plus polarization in the sine quadrature, cross polarization, cosine and sine quadrature. So those are the 4 basis forms. Okay. So, and then now we want to find the best fit values of lambda, that is the coefficients of those things. So this notation is, the usual inner product, the noise weighted inner product we have on data. X was the gravity wave data. So you want to minimize the difference between the data and the signal. So you take dd lambda of this equal to 0, and a little algebra shows you that lambda a, the lambdas are given by this formula. It's, you take the Fisher matrix, and the Fisher matrix is particularly simple here because dHd lambda is just HA, dHd lambda A. So lambda A is just the inverse of the Fisher matrix dotted into the product of the data and HB. Okay? It's this two-dimensional matrix times this vector. Is this vector of coefficients. Okay, so that's very simple. And then if you plug that value of lambda in here, you see that this xx minus x minus the fit, x minus the fit, which is twice the log of the likelihood ratio, just reduces down to this simple expression, the inverse Fisher matrix times xha, xhd, where again the h's are basis functions and x's are data, and gammas are known, they're determined by the basis functions. And that's what we call, so that's 2f. The coherent F-statistic, twice is twice the log of the maximum likelihood ratio after you've optimized. That's what it is. And it's, note that even in the final expression, it's so simple and cute, you don't even have to know the lambda of a's. I use that as an intermediate step, but you can always just calculate this and not even bother to calculate the lambda a's. Okay? So that y equals 2f has a chi-square, has a well-known probability distribution for Gaussian noise, and in fact it's just a chi-square distribution with 4 degrees of freedom. That's 4 because it's a 4-dimensional vector space, and a non-centrality parameter, if there's a signal in there, of rho squared, which is basically the signal to noise squared, HH. Okay, so the probability distribution of y is a chi-squared, 4 degrees of freedom, and non-centrality parameter of the signal to noise squared. And then you can average this over y, and you say the expectation value of 2f over different realizations of noise is just 4 plus the signal to noise squared. And again, that 4 is again just because there are 4 degrees of freedom. Okay, so it's very simple. And if we had, huge amounts of computing power, or even the computing power from like 100 years from now, assuming Moore's law, that's all you would ever need to do all-sky pulsar searches. But we're not there yet in terms of computing power. We're limited by computing power. And the reason is that the number of templates you need to cover the space of parameters, if you're doing an all-sky search over sky position and frequencies and frequency derivatives, scales like something like t to the 5th, right? And another way of saying that is the longer the time scale on which you're looking, the finer and finer the grid you have to use to cover the parameter space, right? And it scales at like a very high power of t. So 10 times longer in t is 100,000 times more difficult in computational power. So what you do then is the obvious thing. You divide the whole observation time t into, say, n pieces, and you do coherent integrations over those n pieces. They don't actually have to be all of the same length, but just for simplicity in my notation, I'm going to assume that they're all the same length, delta t, but that's not required. Okay? So now what is the semi-coherent F-statistic? It's just you take the F-statistic from this delta t, add it to that, add to that, add to that, n times, you just add them all up. Okay? It's called semi-coherent because, well, the whole point again is that if you have some template, it's only required to get a large number of to have this be sizable. The template has to sort of remain in phase up to a constant offset over this range, and then in phase up to a different constant offset in this range, and in phase over this range. So it only has to be in phase with the signal for delta t up to a constant offset. Okay? Okay, so it's easy to show that this, so 2f, I'll write it 2f semi-coherent, SC semi-coherent. So it's easy to show that the semi-coherent F-statistic also follows a chi-square distribution, but now with 4n degrees of freedom, right? So if n is 100, it's 400 degrees of freedom, and the same non-centrality parameter. So the way this one usually thinks of this is to saying, okay, we do sort of coherent integrations, and then we sort of combine that data incoherently. But there's another way of looking at it, which I think is useful. So another way of looking at it is imagine a different search problem. Imagine that the physical signals you were looking for, what you knew was that there was a pulsar up there, and you knew that some aliens or God or something was kicking it every delta t in some arbitrary way. Right? So every delta t, you give it a different h naught, a different I, a different psi, a different phi naught. But you don't know what they are. That's all you know. In that case, there are 4n degrees of freedom, right? And in that case, the semi-coherent F-statistic is really you can show the fully coherent F-statistic. So in this larger space, where you say you don't know, if you imagine that God was kicking it in some arbitrary way every delta t, then that when you calculate would be the fully coherent F-statistic, just with more degrees of freedom. Now the main motivation for the definition for this phase-relaxed F-statistic is just to notice that 4 degrees of freedom per interval delta t is way too many, because God isn't kicking all those parameters. So what's true is that even in nature, for every interval delta t, the h naught is staying the same, right? At least if it's a million-year-old pulsar and you're looking over a year, it's not changing. The inclination angle is certainly staying the same. The polarization is staying the same. The only thing that varies from segment to segment is the relation between what can happen is your template goes out of phase with the pulsar signal. So you need to adjust phi in every segment, but there's no need to keep readjusting the other parameters. So you don't need that many degrees of freedom. What you really need are 3 parameters, h naught, I, and psi, because those are the same everywhere. And then you need n others, all of the phase, one phase for every delta t. So you should be able to do the search not with 4n degrees of freedom, but just n plus 3. Okay? Okay, so that's the motivation, and it'll take me a couple slides now to then define the phase-relaxed F-statistic. So to get there, it's useful first to now, everything I've done has been using a real vector space. It becomes simpler actually, right, to make algebraically if I define complex basis functions. H plus is h1 minus IH3, and h cross is h2 minus IH4. And the reason that's simple is then under a phase shift, phi of t goes to phi of t plus delta, the h cross and h plus transform very, very simply. Whereas the h1 and the h3 would not. Okay? So it's because of their simple transformation that this complex basis is useful. Now that we have a complex basis, we want to also complexify everything else. So instead of using the usual inner product, I'll use a complex inner product, a Hermitian inner product, which looks very much like the usual one, except I have a star there. And then clearly x inner product with y is yx star. And next then we'll define gamma alpha beta as just h alpha h beta. So now this is a 2x2 complex matrix instead of a 4x4 real matrix, and it's Hermitian. Okay? Where alpha and beta, instead of running over 1 to 4, they just run over plus and cross. And then I claim it's just a little bit of algebra to show that then in this basis, 2f, the fully coherent F statistic, is just gamma inverse alpha beta, h alpha x, x h beta. Okay, that's trivial to show. Okay, now I'm going to start to massage that. I'm working my way towards the phase-relaxed F statistic. So this is what I saw at the end of the last page. This is the 2f. And now I'm going to find x of t as just the sum of xi of t, where x of I is the restriction of x is the data, to the ith interval. Right? So x1 of t is just x of t in the first interval, x2 of t is x of t in the second interval, etc. Okay? So x of t then is trivially the sum of I equals 1 to n of xi of t. And then trivially h alpha inner product with x is just the sum over I of h alpha inner product with xi, right? So I've expanded this out into that, okay? And now is where I make the switch, okay? So this would be the fully coherent F-statistic, but now I want to allow for a phase change in every single interval, okay? I want to allow a free parameter in. So I'm changing now, I'm going to a new quantity which also has a phase shift here, e to the I delta I, e to the minus I delta j, okay? You can think of it as changing the phase of either the data by delta I, or changing the phase of the template by minus delta I, okay? But either way, I'm taking the original form and I'm allowing little adjustments in each interval, just forwards and back, just pushing the waveform back and forth a little bit, okay? And now twice the phase relaxed F statistic is then the maximum of this over all of those phase shifts, 1 through n, right? So that is to say, I want to change the phase of the first piece and the phase of the second piece and the phase of the third piece to get maximum overlap, to maximize the likelihood, okay? Just like, so I'm going to be maximizing the likelihood then over these n phases, okay? Okay, and so that was the definition. Let me just, so that is the definition, okay? And so the whole idea then now to calculate this is to find the delta i's, delta 1, delta 2, delta 3, etc. to n that maximize this, okay? So it's basically that take this F statistic and maximize it if you adjust the phases. Okay, so it's sort of adjusting all the phases and then calculating the new F statistic. Maybe that's a better way of putting it. Oh, and by the way, there's one extra degree of freedom here. It's easy to see that if you add a constant to delta 1 through delta n, a constant phase shift to all, then the phase relaxed F statistic remains the same. It's because it's really only the phase differences that matter. But it's actually simpler just to carry along that extra little 1 degree of gauge freedom, just like it's sometimes simpler to work in terms of the vector potential in the magnetic field. So I'll just carry along that extra bit of freedom. Okay? So now the whole game is to calculate these phase shifts, delta 1 through delta n. Okay? And to do that, it will take a little massaging. First I'm going to simplify the expressions and then try to put them in a form where it's sort of obvious what to do. So first thing I do is I take all these phases and I make a new vector out of them. So e to the I, so v I'm defining as e to the I delta 1, e to the I delta 2, e to the I delta n. Okay? And I'm defining a two-dimensional, a two-tensor kji this way, as gamma inverse alpha beta, xjhb, x alpha xi. And if you compare now this to the previous transparency, you can see that it's an exact definition now. I've rewritten the phase relaxed F statistic twice. It's just the maximum over the phases of v dotted into k times v. Okay? V star really, kv. So it looks a little simpler. So the game now is basically to maximize this quantity, vj star kji vi, subject to n constraints, that each of the components of v, well, this one, all have to lie in the complex unit circle, right? That's another way of saying is that v lies on the n torus. So you're maximizing this quantity over the n torus, right? Now how do you do that? Well, the obvious thing when you've got constraints is to use the method of Lagrange multipliers. I have n constraints, so I'll have n Lagrange multipliers. So I just plug this formalism and these equations into the usual Lagrange multiplier formalism. I get what I said before is just equivalent to this. Maximizing VKV, V star KV, is the same as solving these equations. KJI times inner product with VI is equal to lambda J Vj for all j. But I emphasize this, it looks a little bit naively like an eigenvalue equation, but it's not, because it would be if all the lambda j's were the same, if it were just one fixed number. But lambda j is different for every j, right? So and those lambda j's are the n Lagrange multipliers. Okay? So I want to solve this equation now, which I claim is, again, the maximization equation. So how do I do that? I'm going to massage it some more, a little more massaging. So now I'm going to define a projection operator P that takes any n-dimensional complex vector and projects it down onto the unit n torus. That is to say, if W is any complex n vector, where C1 e to the I delta 1, C2 e to the I delta 2, with the C's all real, then P times W just takes all the C's and sets them equal to 1. Okay? So it takes any vector and just puts it back onto the torus. Is that clear? Okay. With this definition, things get even simplified a little bit more. It's now KJ, the Lagrange multiplier equation, it's easy to see, is just now identical to saying that if I operate on V with K, this Kij, and then with the operator P, I just get V back again. They're identical. So I've taken this, what sounds like at first a very hard problem, complicated, and it's just this problem. It's saying I'm looking, so solutions V that maximize the F-statistic are the same as fixed points of the operator PK. Okay? I've purposely led you pretty close to the right answer. So I've massaged enough that I think some of you in the audience, at least, will be able to guess a strategy now for solving for V. Does anyone have an idea?
Again, there's an S calculator or a calculator.
I don't even know what those words mean, so maybe it's the same thing, but I don't know what those words mean. Okay, I'll tell you. So V is a fixed point of this operator, right? You might hope it's an attractive fixed point. If it's an attractive fixed point, then if you iterate on V, operate with PK once, then PK again, then PK again, you'll get closer and closer to the actual fixed point. Maybe it's not an attractive operator and you'd start to move away. Or maybe it's attractive in some directions and not in the others. So it wasn't obvious to me, but this is really easy to code up. In MATLAB, it's much easier just to code up and check than it is to actually, or at least for me, than to try to prove it. And I've done this zillions of times, and it always goes zoop, zoop, zoop to find a fixed point. It's an attractive fixed point, believe me. So all you have to do is start with some V naught that's close enough to the true fixed point, and operate this with many times and go zoop, 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 right to the answer. Now, that's if you start close enough. So I first started, well, maybe I start anywhere on the n torus. And then what happens is sometimes it goes zoop, 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 right to the right answer, and sometimes it gets caught in a 2-cycle. So PK operating on point V1 is V2, and PK operating on point V2 is V1, and the computer goes crazy going back and forth, back and forth, back and forth between them forever. Okay? So that's the behavior I found if you just start anywhere. But if you start, make any kind of reasonable guess for V naught, then it goes, every single time I found it goes zoop, zoop, zoop right to the right answer. And what's my guess that works? Well, for every single of those intervals, delta t, delta t1, delta t2, delta t3, you can calculate the F-statistic just for that alone. Get parameters ai, iota I, psi I, phi I for that interval all by itself. And if you use phi I as just a guess for that interval, right? Each interval you use just the information that interval alone as the initial guess, then in my experience this always converges fast. Whereby fast I mean say n is 10, then in about 30 steps it's at the right answer within 10 to the minus 8. Okay? So that's the method, and I'm almost done. So I have this new statistic, which I think is closer to the physical problem than the old one. I've shown you it's not so hard to calculate, And now here's an example of now comparing in power, in sort of statistical power, the semi-coherent versus the phase-relaxed F-statistic.
It converges here for noise alone, for noise only.
I think it did, yes. Well, yeah, absolutely. It converges even for noise only. Absolutely, it does. Yeah. A little surprisingly, but it does. Yeah, exactly. It does. At least it always has in many, many thousands of tries. Okay, so for this one comparison, I just imagined, I took kind of arbitrarily, pseudo-randomly, I mean out of my head, I just took some pulsar signals and some position on the sky. Then I imagined scaling the distance, just so I can get a range of rho value, of signal to noises. And I imagined looking for it with both the semi-coherent F-statistic and the phase-relaxed F-statistic, assuming with a kind of a worst-case scenario that my template was so bad in phase that the phase difference between my template and the true signal was just absolutely random in each n. So I chose a random number. So it's the worst-case scenario in terms of phases. And I chose an n equals 100, so like the 100-day integration each one day right. Okay, and now I plotted. So give a detection statistic for any threshold, you get a false alarm probability. How often you get above that threshold by accident, by luck or something. And given a threshold and a signal strength, you also get a false dismissal probability. How often the signal is really there, but your threshold's so high you don't see it. Okay? So then given a signal strength, you can draw a curve in this plane, in the FA-FD plane. This is equivalent to what's usually called the ROC curve, the receiver operator characteristic, though it's, I changed the axes compared to other people. And I like plotting the log 10 of F because this tends to vary, FA tends to vary a lot. And I looked at the case rho squared, signal noise squared, 75, 100, and 125. And then for both statistics, so blue is the semi-coherent statistic, and green is the phase-relaxed statistic. And for any false dismissal probability, you just compare the false alarm probabilities, right? And green is better, right? And sometimes much better by a few orders of magnitude. Okay? So that's good. Oh, the way I did this, so I just did the search, so I had one pulsar, and then I took 10,000 realizations of the noise. And from that was able to basically draw these curves. Okay, something I'm not going to show you is then, so it shows you the relative false alarm rates for the same false dismissal rate and the same signal to noise. You can ask, how much do you have to adjust the signal to noise, so of the signal, so that say the semi-coherent approach is looking at, so that it has more or less the same ROC curve as the phase-relaxed F-statistic in your original signal. So I played that game. So how much would I have to raise the signal to noise of here to make the blue go down to the green, basically, the light more or less on top of it? That's roughly like 10 to 15% for this one example. And that's why I said I was guessing like roughly a 10 to 15% change, but that's just one example. I should really do it based on one pulsar and 10,000 realizations of the noise. I really have to do a Monte Carlo, and I will. Okay? But that's just to give you a rough idea.
So the threshold you find it empirically, right?
No. So for every one, I can see what the threshold is, right? Oh, sorry. So the threshold, so you vary the threshold, and that's like varying the false alarm rate. Okay. Right. Okay, and this is still sort of early days, but what I thought was, I introduced something, and I showed at least plausibly it's quite a fair amount better, or at least enough better than what's usually used to be worthy of more interest. Searching. So the things I want to do next are try to incorporate it into real searches, real LIGO Virgo searches. I showed you one way of converging quickly to the right answer, but I bet you there are even faster ways. If maybe you divide up the whole signal into two pieces, and then do converge on those. I bet you there are many ways you can imagine speeding up that convergence even faster than. I didn't try. Once I found one good way, I didn't try to optimize it. You can imagine using this not just for searches, but for vetoes. So for instance, with this statistic, you can see whether, if you analyze the first half of the data and the second half of the data, whether H0 iota psi for the first half is consistent with H0 iota psi for the second half. That would be a new veto. Something else you might do is just along the way of calculating this F-statistic, you get all these values, delta 1, delta 2, delta n. So you see how your template is moving away from the data. If you imagine fitting to that, then you can jump very quickly to improved spin down parameters. I haven't tried it, but I'm going to try it soon. I think it probably should work. And lastly, I've been talking just about gravity wave pulsars, but this will also work for non-processing binaries. A circular non-processing binary has the same gravity wave signal as a pulsar, basically, as a very rapidly chirping pulsar. Chirping in the other direction, because the frequency is going up, not down. Okay, so you could use this to search for anything that's any very long chirping binary. For instance, I'm interested in BBO, where you look for neutron star binaries that last a year. You could use this same thing, or the Einstein telescope, for which neutron star binaries will also be in there for a considerable length of time. So anytime you're looking for circular orbit non-processing binaries, and where you're computationally limited, you could use this trick. Okay, and that's all I wanted to say. I think I was even half an hour. Yeah?
How about the number of intervals? You showed us one case, right, for 100.
Yeah.
And that's picked, it has something to do with the signal lines.
Oh, I just picked that number because that's what's typically a typical number in the real LIGO Virgo searches. Typically, n is order 100. So I didn't adjust it much. I should really explore the whole parameter space. That's just a kind of typical number. That's yes, that's right.
If you choose 0, so the static cluster.
Yeah. Then all the deltas would be approximately 0, except for little noise corrections. All right. That's
yeah, but do you have sense of
part?
How much improvement that you get over the central mirror?
I'm sorry, I don't quite understand the question.
Like, do you have a sense of how much improvement you get over the central mirror?
See, it doesn't matter what they are. That's the whole point. I mean, whether they're 0 or anything, you get the same improvement because the deltas go to the right answer. So saying they start out as 0 or saying they start out randomly, it doesn't matter. It's the same. You'd get the same number. So it's the same improvement you've just seen. So no matter whether it's random or right on, you're going to get the same number. I've certainly thought of that, and I don't think it. I think it's about the same. I certainly have an argument that's about the same, but I'm pretty sure it is because I have an argument. But I should really demonstrate it by actually just doing it, by actually looking at, by plotting how f changes as you change the parameters. I'm very confident it's about the same.
The second performance is that if you look at the Einstein home search, it's the last one, it's 5, and they're still analyzing.
Yeah.
It used 80 segments of 40 hours each.
80.
And a 40-hour segment is fetched up from SFTs, which are half an hour long.
Yeah.
So it has 80 pieces of data inside.
Yeah.
So if you want to use your approach, then the computation of individual F-statistic, individual small pieces,
Yeah.
would require something like 80. As then you have another 80 pieces that you need to operate, so you have to be all the number of iterations you have marked specification very tightly.
Yeah.
Otherwise, the time you spend computing.
Oh, sure. Yeah. That's true. So that's why I was saying things. So I'm suspecting, right. So the question is how much extra computational power it does it. It obviously takes more computational power to compute this than the semi-coherent. However, the sensitivity to the semi-coherent doesn't go up very fast with computational power. So I don't think a factor of 10 or something is going to change that comparison of 10%. Secondly, I think you're going to win back quite a lot of that computational power by the fact that it gives you all the delta 1 through delta n's, and so you can, instead of then refining and refining and refining, you can probably go almost directly to the right spin down parameters. But that's another reason I didn't say why the 10 to 15% was rough, because it depends exactly how you actually use it, right? It depends. You'll probably have some, a hierarchical search, and this will be one stage in it or two stages in it, and it depends exactly what role it plays to see how much it improves. And you're right. Part of that is how many times. You have to, how many operations it takes to converge the delta. That's what actually part of what I meant when I said there are probably lots of tricks for reducing the number of steps, also for reducing the size of the matrices. So you start with, say, the first 10 deltas and the second 10 deltas, and have those converge, and then things like that. So I suspect there's money to be made, or cycles to be saved, but I don't know exactly how much, certainly. But your point is well taken. Yeah, Nick. Okay.
Such a thing as a fixed point combinator.
Oh, I didn't know that. Okay.
Computer science.
Uh-huh.
And there's
Thank you. Thank you very much. I'm going to go Wikipedia that as soon as this is over. Fixed point combinator. That sounds like really good. Okay.
Say pk minus n.
Yeah.
Did I get back to that?
Well, it's pk minus, you say, well, pk minus, you want a 0 of that, right?
Minus 1 would be, yeah.
Yeah, you were looking for zeros of that operator. I'm not,
Shrink, is it?
that would shrink. Yeah, it would shrink. Yeah, that might actually be, I don't know, would that be a better thing to do computationally? I don't know.
No, I think that just
It's the same.
where you converge always.
Yeah. That's a good idea. I can check that. It's a nice rewriting. I'm sorry about the questions now. I'm cutting into Michaela's time terribly, so.